So I'm Yuri Galindo. Me and my colleagues were working on filtering false positives from the captures made by the Axis network. Okay, so I'm going to focus on our main contributions that are, we corrected the methodology that we were applying for this task, and we managed to correct the probabilities that the network assigns in order to improve our results. So just to give you a perspective, the images that we're using are produced by the UFO capture software. So it's a summary of a video, and we're using these images to try to filter the false positives. Okay, so the model that we use in our convolutional neural networks, and the way a convolution is an operation that we can do between a filter and an image in order to extract features. And so they work by stacking these filters so that the first ones learn more basic things and the later ones are trying to detect more complex things. And it's important to know that these filters, they are not set by humans, they are learned. So what we do is we give the model a bunch of images from meteors and images from false positives, and it will try to learn the better parameters. And so when we're dealing with this kind of model that learns based on data, we have to train it in order for it to learn, and then we have to test it on new data, because what we want to know is how it behaves on new data. So here we have an example in the left, something that the model might have learned, and in the right, it may be the case that this thing that it has learned does not generalize well. And this is where our main contribution comes from. Our first contribution is that the captures made by the software, there may be hundreds of captures from the same event. So here we have, it's a collection of 72 captures. So each one of these is a whole video that is summarized as an image. And so these are different videos. And if we randomly separate the training and test images, that is the standard practice, and it's what we were doing and other groups were doing as well. It may be the case that some of these end up in training and some of these end up in test. And it's not ideal because we want to know how the model will behave to new images, not to images that it has seen before. So let's say that, for example, two of these images ended up for testing. It may be the case that the model has only memorized the images, and even so it will get the correct answer. So we did an experiment on trying to predict false positives on images from new dates. So for example, training up to 2019 and testing how it works on 2020. And the performance was lower than what we would expect by randomly separating. So it was supposed to have 98%. So, but actually when predicting on new images, it has 94% accuracy. And there's another factor is that Axis has over 50 stations around various parts of Brazil, in which each one of them has a different profile. So different kinds of false positives. So it may be the case, for example, that a network that was trained only on the left kind of images that are from airplanes. So it might have learned, for example, that the false positives are straight and bright lines. And when it saw a different object, like the examples on the right, it would think maybe that it is a meteor. But what we want is that the model behaves even for new objects. So we have to test for that. Because even on every region will have false positives that are new, things that haven't happened before. And so we also did this experiment trying to predict on images from new regions, and you saw an even greater drop. And we also saw an increase in standard deviation. So when separating randomly, it doesn't make a lot of difference which images you have chosen for tests. But with regions, we can see that some regions are harder and some regions are easier to predict on. But we can see that the model has a problem when trying to identify new objects that it hasn't seen before. And so we had to deal with this problem, and our solution was trying to automatize the most confident images. So for images that the model gives us a high probability of being a meteor or a high probability of not being a meteor, we could automatize them. And the other ones that are below this confidence threshold, it would remain for human inspection. So we did this with over 99% confidence, and it used 70% of images and improved accuracy to 94%. But since we're using 99% confidence, the expected thing is that we would have close to 99% accuracy, right? So it's not ideal. And this happens because the model is miscalibrated. So this is an example of the confidence assigned by the model. So we can see on the left that most of the predictions are given close to 100% confidence. And here we can see that these are the confidence levels and the accuracy that it actually achieves and the accuracy that it was supposed to achieve on this confidence level. And we can see there's a big gap. So our idea to fix this and actually get reasonable confidence levels is to have a second model. So this model is based on the predictions of the first model, and it corrects the probabilities to give us right probabilities. So we separate the data, and since we want the right probabilities to a new region and new objects, we separate these 3 partitions, each one with different regions. So one for training the calibration, and the other one for testing. And with this technique, we saw a big improvement in without any calibration, the regular model, with 99%, it gave us 94% accuracy. And the calibrated model, with 99% confidence, it actually achieves 99% accuracy. And for lower level of confidence, we still see high accuracy, and coverage means the percentage of the images that are going to be automatized. So we also see we have better choices. So here in the uncalibrated model, we have 70% of the images, we had 94% accuracy. And with the calibrated model, with the same percentage of images, we can maintain higher accuracy. So it managed to greatly improve our results. And it gave us more fine-grained control, and better options. And then and this is a model that is considerably reasonable. It has 98% accuracy, and it predicts on over half the images. So it would manage to reduce the work for manual inspection while still maintaining high accuracy. And then after we know how well the model performs, we can do the final round of training. So we can use most of the images for training and some for calibration, and then finally use it in practice for filtering the false positives. So this concludes the presentation. I have here the attributions for the images and the icons that I have used. All the surveillance images come from the Axis project. And here are some related works on also classification of false positives from Meteor surveillance programs.
Thank you. Apparently that was your last, wasn't it? Yeah.
Was?
Yeah. Well, this was your last slide, wasn't it?
Yeah.
Yes. Thank you. You know, it's difficult when people are in the large audience room, you can hear the clap. But when there are no people around, you don't hear the clap. So is there anyone who can react to this interesting talk. Jim Rowe, at least not muted. Circo. Okay, so
Yuri,
Circo.
did I get you right that these data were trained on CAMS data? Though my question would be, how well do you believe would it generalize to data from other cameras?
Yeah, so I think it depends on how different are the images captured. Because apart from the different objects, we will also have more different things, right? Like the lens is probably going to be different, and the kind of image, it may have more color, this kind of things. I think we would have to test how well it works. But I think that the idea of calibration would probably can be applied to other programs we found.
And the input was plain some image from Meteor, so no extra input vector that you somehow calculated the image in survey. It was really the plain image. That's what you trained. Okay.
Yes, solely the image.
Mm-hmm.
Yeah.
Thanks.
All right.
Question.
Yep.
Do you think this is the general idea of the system to post-produce the data, or do you also think about live analyzation?
Yeah, so I think the model can be applied to both in both ways. I think we're still trying to see how we will use it, but I think it's more a problem of resources, and because if we can actually make it work live or not, I think we're going to know that only on the future. But it can be applied on both ways, theoretically.
So you need enough calculation time, so something you do after the recording of any event that could be a meteor or something else.
Yeah, so maybe it depends on how many computing power we have. Like theoretically, we can do it live, but I don't know what are the resources we're going to actually have. But it's doable.
Thank you.
How big does a training data set need to be? I mean, to train a new model, for example, on our All-Sky 7 cameras, how many false positive, false negatives would you need to train the model?
Yeah,
roughly?
So the data that we used has about 2,500 of each. We have about 5,000 images on total. But I believe that if we had more images, it would be better, even better. So I think 5,000, 4,000, it's the minimum, I think. But
okay, but that's manageable. I mean, with a single camera, we recorded 5,000 meteors a year, so that should be fairly simple to provide such a training data set. Thank you.
Yeah.
Yeah. Thank you.
Like
It's
you
time
also
to
want
move on.
to have the false positives there, then.
Can you repeat, please?
I'm sorry.
And there was a comment to what Zirko was saying. I mean,
Yeah.
you also need to have the false detection.
Yes, we need to keep the data which we are throwing out at the moment. We need to store them in order to train the model. That's you're right, of course.
Yeah, I think that storing the false positives is it's very important, because since there are a lot of false positives examples, we need to have some diversity.